All right, every developer has been here. You've got an app, it's out in the wild, and the reports start coming in. It's slow, it's buggy, users are unhappy. Today, we're putting on our detective hats to solve one of these classic cases, the mystery of the slow Android app. So, let's get right to it. Our crime scene is a mobile application, and the victim, the user experience. We're talking about a slow, unresponsive app that freezes, stutters, and is basically frustrating everyone who uses it. Our mission is to follow the evidence, interrogate the suspects, and find the root cause of this performance crime. You know, every good investigation starts by securing the crime scene, and for us, that scene is the user's screen. The first reports are not good. The app is freezing up, especially when the user is scrolling or interacting with it, and people are, well, they're getting pretty annoyed. And here's our smoking gun, the dreaded application not responding dialog, the ANR. If you're an Android developer, this screen sends a shiver down your spine. It's the ultimate sign that you've blocked the app's main thread for way too long and the operating system has officially lost its patience. This is bad. Now, the forensic data backs this up completely. We're looking at a huge spike in what we call janky frames. Just think of these as stutters. It's when the app can't draw a new frame fast enough for the screen's refresh rate, so the animation just jitters. A decent app might see maybe 15% jank. Our victim here, it's hitting almost 38%, and older versions were over 50%. There's no doubt about it. The user experience is broken. Okay, so we have our evidence. But any good detective knows you can't just jump to conclusions. It's time to line up the usual suspects, the common criminals behind these kinds of performance issues, and check their alibis one by one. First up, let's look deep into the system. Could this be a low-level problem? Maybe a bottleneck in how the app is managing its memory? This is often a really tricky, deep-rooted kind of issue. So one theory is something called an atomic lock on memory. You can picture it like a one-lane bridge where all the cars, or in this case, all the threads, have to line up and wait their turn to cross. It creates a massive traffic jam. But looking at this app's code, we see the developer has what's called deterministic control. They're manually managing memory, which is more work, but it avoids these kinds of jams. So suspect number one, cleared. All right, on to the next one. What about the most common offender in the entire Android ecosystem? A heavy background task that's blocking the main UI thread. Honestly, this is suspect number one in 99% of these ANR cases. We took a hard look at how the app's background threads talk to the user interface. A classic mistake is to use a blocking call, like synchronize, which basically makes the background work grind to a halt until the UI is free. But nope, a quick look at the code shows they're using queue. This is the right way to do it. It just sends a message to the UI and says, hey, get to this when you can without stopping everything. So our second suspect is innocent too. Okay, so the obvious suspects are in the clear. Our investigation has to go deeper now, into the app's own logic. And that's where our search leads us to a very specific, and as it turns out, very deadly, piece of code. A loop that's dynamically creating hundreds of UI controls. And here it is. We found the weapon. It's inside a tight loop that's building a big grid of items. And inside that loop are two seemingly innocent lines of code. One updates a progress bar. The other updates the Windows title. But here's the thing. It's doing this on every single pass of the loop, forcing the entire screen to try and repaint itself over and over and over again. The impact is just staggering. We attached a profiler to this loop, and the results are pretty damning. It takes over 10,000 milliseconds. That's more than 10 seconds to finish. For 10 seconds, the UI thread is completely maxed out, the screen is frozen solid, and the user is just sitting there, tapping the screen, wondering what's wrong. We've got our culprit. So now that we've identified the guilty code, let's talk about the solution. And it's an incredibly powerful, elegant pattern that every senior developer should have in their toolkit when they're building complex user interfaces. This pattern is called begin update and end update. And really, what this is all about is respecting the UI thread. When you call begin update, you're basically telling the UI control, hey, hold on, I'm about to do a bunch of work. Don't redraw yourself, don't recalculate your layout, just wait. Then you can go ahead and add hundreds of items, change all their properties, do all your heavy lifting. And when you're done, you make one single call to end update. And only then does the control repaint itself, just once, with all the changes applied. You're batching all that work into a single efficient operation. And the process couldn't be simpler. Right before your loop starts, you call begin update. Then, inside the loop, you do all your work, creating and adding your controls just like before. And after the loop is totally finished, you call end update. That's it. The UI, which was patiently waiting, then redraws itself exactly one time with everything perfectly in place. And now for the moment of truth. Let's look at the verdict. We're going to put the original guilty code right next to our new clean code and see the undeniable proof of this change. On the left, you see the offender, that loop with the progress bar and caption updates inside, just hammering the UI with repaint requests. And on the right, the clean code. The core logic is exactly the same, but it's now beautifully wrapped in that begin update, end update block. And of course, we took out those useless progress updates from inside the loop. And the result? I mean, wow, it's nothing short of spectacular. We go from over 10 seconds of a totally frozen app down to just about 100 milliseconds. That's literally 100 times faster. The app is no longer janky, it's fluid, it's responsive, it feels like it's supposed to. Case closed. So the case might be closed, but the lessons we learned here are what really matter. These are the principles that are going to help all of us prevent these kinds of performance crimes in our own apps down the road. So here it is, your Performance Detective's Handbook. First, always batch your UI updates. Anytime you're adding a bunch of items to a list or a grid, begin update and end update should just be second nature. Second, never, ever update things like progress bars inside a critical loop. Just don't do it. Do that stuff outside the loop. And finally, the most important rule of all, always measure. Don't guess where your performance problems are. Use a profiler. Get the real data, because the data never lies. And this whole investigation leaves us with a really fascinating question to think about. You know, as our tools give us more and more control over performance, all the way down to memory and threads, that line between being a regular app developer and a low-level systems engineer, it's starting to get pretty blurry. And how we as developers handle that growing responsibility is really going to define what great software looks like in the future.